Welcome to Coast CCNA Learning, your complete guide to conquering the Cisco Certified Network Associate exam. This video dives into CCNA Topic 1.2, Network Topology Architectures, where we move beyond individual devices and look at how networks are actually built. We'll explore the layouts and design models that define how routers, switches, access points, and other components connect and interact. From campus LANs and data centers to WANs, branch offices, cloud networks, and even SOHO environments, each architecture serves a specific purpose. Understanding these topologies helps you see how networks are structured to support performance, scalability, and reliability, all essential in real-world deployments. By the end of this video, you'll be able to recognize and describe common network architectures and understand the design decisions behind them. Let's dive in and see how everything fits together. Let's start by understanding what a LAN, or local area network, actually is. A LAN is a network that connects devices within a limited area, such as a home, small office building, or a campus with multiple buildings in one location. These networks are built to support a handful of users and devices, offering reliable connectivity without the complexity of larger enterprise networks. SOHO networks are everywhere, from the Wi-Fi in your home to a local coffee shop's wireless setup, or even the network in a small boutique retail store. These are all examples of SOHO networks, where simple and cost-effective networking solutions are essential. Typically, a SOHO network relies on a single Wi-Fi router, a device that combines the functions of a router, switch, and wireless access point all in one. This router connects the network to the internet, provides wired ports for desktop computers or printers, and broadcasts Wi-Fi for laptops, smartphones, and tablets. Because it's an all-in-one device, setting up a SOHO network is straightforward, even for users without deep technical expertise. Security features like built-in firewalls and Wi-Fi encryption help protect the network from common threats. While SOHO networks are smaller and simpler than enterprise networks, they still rely on the same basic components and networking principles you'll continue to build on throughout your CCNA journey. Let's consider a medium-sized network, for example, a network in a retail store or a small medical office building. These environments support dozens or even a few hundred users. They need to connect multiple subnets, provide reliable Wi-Fi, and ensure devices like phones, printers, and security cameras can all communicate efficiently. These networks require more than just a simple Wi-Fi router. They start to rely on switches and a more structured design to handle growing traffic and maintain performance as the number of devices increases. And as we move beyond that to larger enterprise networks, things become even more complex. Now we're talking about hundreds or thousands of users and devices spread across multiple floors of a high-rise building, or even an entire campus. These networks need to handle high traffic volumes, provide resilience against failures, and be flexible enough to grow as the organization grows. That's where campus LAN architectures come in. Campus LAN architectures are built using either a two-tier or three-tier model depending on the organization's size and scalability needs. A two-tier architecture, also called a collapsed core, is common in small campuses with a single building. The two-tier model merges the distribution and core functions into a single layer, hence the name collapsed core. It's a simpler, more cost-effective design suited for environments where a separate core layer isn't necessary, yet performance and redundancy are still important. A three-tier architecture is designed for larger, more complex environments, such as large sprawling campuses, like those seen at large hospitals or universities. The three-tier model introduces a dedicated core layer. This core serves as the high-speed backbone of the network, interconnecting multiple distribution layers and enabling fast, resilient communication between buildings and departments. The function of each layer is important for the CCNA, the access layer. This is where end-user devices like computers, phones, and printers connect to the network. Layer 2 switches and wireless access points are part of the access layer, the distribution layer. This layer connects multiple access layer switches, applies security and routing policies, and provides routing between VLANs. The core layer is a high-performance, low-latency backbone connecting distribution layer switches across the campus for optimal speed and fault tolerance. Two-tier is ideal for networks within a single building or smaller footprint, where simplicity and cost savings are priorities. Three-tier provides the scalability and resilience needed for large, multi-building environments with heavier traffic demands. So as we transition from SOHO and medium-sized networks into the world of campus LANs, we see how network design evolves to meet greater demands for performance, reliability, and flexibility. Whether it's a two-tier or a full three-tier architecture, these models provide the foundation for building networks that can scale as organizations grow. As networks continue to grow in complexity and scale, the design of the data center network becomes critically important. While a campus LAN connects users and devices across offices and buildings, the data center architecture focuses on connecting the servers, storage systems, and services that power business applications, cloud platforms, and enterprise workloads. One of the most common modern data center designs is the spine-leaf topology. Let's break down what that means and why it's become a standard in today's high-performance data centers. Imagine a data center filled with racks of servers, storage devices, and appliances. These systems need a network that can deliver fast, predictable, and scalable connectivity because applications depend on moving huge amounts of data between servers, often in real time. In a spine-leaf topology, the network is organized into just two layers. The leaf layer, where all devices in the data center, such as servers, storage systems, and other network appliances, connect. Think of these leaf switches as the access points into the network fabric, and the spine layer, which consists of high-speed, high-capacity switches that interconnect all of the leaf switches. Every leaf switch connects to every spine switch, creating a full mesh between the layers. This design ensures that any server or device connected to one leaf switch can communicate with any other device across the fabric in exactly the same number of hops. That means predictable latency and consistent performance, no matter where workloads are located in the data center. Spine-leaf architecture has several advantages. Scalability is one advantage. Need more capacity? You can simply add more spine switches or more leaf switches as your data center grows. The design is modular and easy to expand. The full mesh connections between spine and leaf switches means there are no bottlenecks at the core, assuring high bandwidth so that traffic can flow smoothly between devices. In older data center designs, most traffic flowed north and south. That is to say, between a server and a user on the outside, passing through the data center's core to reach the internet. But in today's data centers, most of the traffic flows east and west, meaning traffic moves between servers inside the data center. This could be database servers communicating with web servers, storage systems syncing data, or virtual machines talking to one another. Spine-leaf architecture is designed for this, providing a consistent number of hops and low latency for all devices in the data center. With only one spine switch between any two devices, you get consistent, low-latency performance that modern applications demand. Traditional three-tier data center designs, with access, distribution, and core layers, often introduced bottlenecks as traffic had to pass through multiple layers. Spine-leaf flattens the architecture, making it ideal for east-west traffic patterns and high-bandwidth server-to-server communication. In summary, spine-leaf topology is the backbone of modern data center networks. It supports the massive east-west data flows driven by virtualization, cloud computing, and distributed applications, all while providing scalability, performance, and reliability. So far, our focus has been on traditional on-premises architectures, networks where all infrastructure is physically located at an organization's site. That includes routers, switches, servers, storage, and security appliances. Everything is installed and managed by the internal IT team. This setup provides full control over performance, security policies, and compliance. However, with that control comes responsibility, including power, cooling, maintenance, upgrades, and physical security. In contrast, cloud architectures shift much of the infrastructure off-site. Instead of building and managing an on-site data center, organizations rent resources such as computing power, storage, and network services from providers like AWS, Azure, or Google Cloud. The cloud provider manages the hardware, power, cooling, and physical security, while the organization retains control over applications, data, and configurations. The cloud offers clear advantages such as scalability. Resources can be easily scaled up or down as demand changes. The cloud provides global reach as applications can be deployed closer to end users. And the cloud also simplifies operations by offloading hardware maintenance and upgrades to the provider. One clear example of how cloud architectures have transformed network design is the DMZ, or demilitarized zone. Traditionally, in on-premises networks, the DMZ is a special isolated part of the network that hosts public-facing services, such as web servers, email gateways, and file servers. It is protected by firewalls and access controls, which act as a buffer between the public internet and the private internal network. Today, however, many organizations have moved these public-facing services to the cloud. Instead of hosting a web server in an on-site DMZ, cloud-hosted web servers, APIs, and applications are now commonly used, protected by cloud-native security tools like security groups, web application firewalls, and DDoS protection. Cloud environments can be public, private, or a combination of both, known as hybrid clouds. Public clouds are accessible over the internet, private clouds are restricted to authorized users, and hybrid clouds blend the two to meet specific security, performance, or compliance needs. Cloud services are typically delivered in three main models, each offering different levels of abstraction and management responsibility. In Infrastructure as a Service, or IaaS, organizations rent virtualized computing resources, such as virtual machines, storage, and networking, while retaining control over the operating systems, applications, and data. This model closely resembles traditional on-premises infrastructure, but without the need to manage physical hardware. Providers like AWS EC2 or Azure Virtual Machines are examples. Platform as a Service goes a step further by managing not just the infrastructure, but also the runtime environment, including operating systems, middleware, and application frameworks. Developers can focus solely on writing and deploying code without worrying about system administration tasks. Examples include Google App Engine, Azure App Service, and AWS Elastic Beanstalk. With software as a service, users simply access the software through a web browser or client interface with no need to install, maintain, or update anything locally. Common examples include Microsoft 365, Salesforce, and Google Workspace. SaaS enables rapid deployment, simplified management, and minimal maintenance, making it ideal for a wide range of business applications. These service models allow organizations to choose the right balance of control, flexibility, and operational simplicity, whether they want to build custom applications, develop rapidly on managed platforms, or simply consume ready-made software. Moving public services to the cloud can reduce the attack surface of the on-premises network. With fewer systems directly exposed to the internet at physical sites, the number of potential entry points for attackers is reduced. The cloud provider's security controls and global edge infrastructure can help shield services from threats at scale. In addition, the cloud offers scalability, flexibility, and global reach that is difficult to replicate with on-premises hardware. On-premises architectures provide control and help keep sensitive systems close, but they require more hands-on management. Cloud architectures offer flexibility and scalability, offloading hardware management and extending the security perimeter beyond the physical site. Most enterprises today adopt a hybrid approach, blending on-premises and cloud resources to balance control, cost, performance, and security. We have talked a lot about LANs, which connect devices inside a building, a campus, or a data center. LANs provide high-speed, low-latency communication using technologies like Ethernet and Wi-Fi. They're entirely owned and managed by the organization that uses them. But what if you need to connect multiple LANs together over large distances? Say, for instance, between offices in different cities, states, or even countries. That's where the Wide Area Network, or WAN, comes in. LANs connect devices within a small localized area. They are fast, easy to manage, and under full control of the organization or homeowner. A WAN connects those LANs over long distances. WANs rely on telecommunications carriers or internet service providers who own the physical infrastructure, like fiber optic cables, satellite links, or cellular networks that span those distances. So while a company usually owns its switches, routers, and cabling, it typically leases or subscribes to WAN services that connect its different locations together. Let's say a company has a headquarters in Boston with branch offices in Chicago, Dallas, and Los Angeles. Each office has its own LAN, but users at all of those sites need to access shared resources like centralized applications, file servers, or databases and communicate with one another securely. That's what's known as a branched network, where multiple remote sites or branches connect to a main location, often called the headquarters or central office. The WAN is what connects all of these LAN branches, creating one unified network even though the sites are geographically separated. Now, how do we actually connect these sites over the WAN? There are several access methods that you'll see in the real world. Branch sites located in metropolitan areas can often connect using high-speed Ethernet links provided by carriers. This is called Ethernet WAN or Metro E. It feels like an extension of the LAN over the WAN infrastructure. A lot of businesses use standard internet connections like cable or DSL combined with VPNs or virtual private networks. VPNs encrypt the traffic, securing communication over public internet links. Broadband connections such as these are the most common WAN connections for homes and SOHO networks. Cellular is sometimes used for remote sites, especially for temporary branches and mobile offices. Cellular is also commonly used as a redundant backup link. In very remote areas where other services aren't available, satellite links can provide connectivity, though typically with higher latency. Multi-protocol label switching, or MPLS, is a popular WAN transport service offered by providers. It enables private, secure routing between sites across the provider's backbone. MPLS works in combination with various access technologies such as broadband, fiber, or even cellular to deliver reliable enterprise WAN connectivity. WANs can be built using different topologies depending on how the sites need to communicate. The most simple WAN topology is the point-to-point network, where two sites have a direct logical connection with each other. Hub and spoke is another common WAN topology where all branch sites connect back to a central site or hub site, usually the company headquarters. All traffic between branches flows through the central site. It's fairly simple, but can create bottlenecks at the central site. One benefit of the hub and spoke model is that it allows for security policies to be easily implemented for each branch site. In a full mesh topology, every site has a direct connection to every other site. This provides maximum redundancy and direct communication paths, but can be costly and complex to configure and manage. A partial mesh is a hybrid between hub and spoke and a full mesh, where some sites have direct links between each other, while others rely on the central office site. It is less expensive and complicated than a full mesh and allows the organization to prioritize fault tolerance for mission-critical sites. These designs are chosen based on the business needs and performance requirements, as well as the needs of the budget. So to summarize, LANs connect devices within a building or campus under the direct control of the company or owner. WANs connect those LANs across cities, states, and countries using carrier services and shared infrastructure. WANs are what connect branched networks, giving remote offices access to the same resources and services as the headquarters. WANs use various access methods like dedicated fiber optic, metro Ethernet, or broadband and can be designed in different topologies like hub and spoke or mesh to meet business goals. Before we wrap up network topology architectures, let's have a look at some examples of questions you may see on the CCNA exam from this topic. This question asks, which two functions are performed by the core layer in a three-tier architecture? And we're told to choose two. Let's go through the options. A. Police traffic sent to the edge. No, policing traffic is a QoS mechanism that is typically handled at the distribution or access layer. B. Ensure timely data transfer between layers. Yes, the core layer is responsible for fast and efficient data movement. C. Provide uninterrupted forwarding service. Yes, high availability and quick forwarding are core layer priorities, and that is our two, but let's continue to look at the last two choices. D. Provide direct connectivity for end-user devices. No, that's the role of the access layer. And E. Inspect packets for malicious activity. Deep packet inspection or threat detection is typically performed by security appliances or at the distribution layer, not at the core, which avoids processing intensive tasks to maintain high performance. So the correct answers are B and C. This question asks, which function is performed by the collapsed core layer in a two-tier architecture? In a collapsed core design, the core and distribution layers are combined into one. Let's go through the options. A. Enforcing routing policies is correct. This is a function of the distribution layer, and in a collapsed core setup, that responsibility is included. The collapsed core handles routing decisions, including inter-VLAN routing. Let's continue with the other options. B. Attaching users to the edge of the network. No, this is the job of the access layer. C. Applying security policies. No, While the collapsed core may implement some basic access controls, applying security policies broadly is more closely tied to the access layer or dedicated security appliances. This option is too general and not the best fit. Option A is better. D. Marking interesting traffic for data policies. This is partially true. QoS marking can happen at the distribution layer in a three-tier model, especially for prioritizing voice traffic before it hits the core. So, in a collapsed core, this function could occur, but it's not a primary role of the collapsed core. Option A, enforcing routing policies, is a more fundamental function of this layer, which is why A is the answer. What is a characteristic of spine and leaf architecture? Let's look at the options. A. It provides greater predictability on STP-blocked ports. No, spine and leaf architectures are usually built to avoid spanning tree protocol altogether by using layer 3 routing between switches. So, blocked ports due to STP are not a concern in this design. B. Each device is separated by the same number of hops. This is true and is a defining feature of spine and leaf. Since each leaf switch connects to all spine switches, traffic between any two devices always travels a consistent number of hops. We should always look at all options, so let's continue. C. Each link between leaf switches allows for higher bandwidth. No, leaf switches do not connect directly to each other. And D. It provides variable latency. One of the advantages of spine and leaf is its consistent latency, thanks to the consistent hop path between devices. But what is a function of a hub-and-spoke WAN topology? In hub-and-spoke, all traffic between spoke sites goes through a central hub site. A. Supports application optimization. While WAN optimization can be implemented within a hub-and-spoke topology, it's not a function of the topology itself. B. Provides direct connections between subscribers. No, this describes a mesh topology, not hub-and-spoke. C. Supports layer 2 VPNs. This is more dependent on the underlying WAN technology than the topology itself. Hub and spoke can be implemented over different types of VPNs, including layer 2 VPNs, but supporting layer 2 VPNs is not specific to this topology. D. Allows access restrictions to be implemented between subscriber sites. This is a key advantage of the hub and spoke design and the correct answer. An organization has decided to start using cloud-provided services. Which cloud service allows the organization to install its own operating system on a virtual machine? Let's see which option is best. A. Platform as a service. No, this provides a platform allowing customers to develop, run, and manage applications without managing the underlying infrastructure, including the operating system. B. Software as a service. Software as a service delivers software applications over the internet managed entirely by the provider. Users just use the software, not the operating system. C. Network as a service. This provides network services virtually, not related to OS installation on VMs, and it is not a standard CCNA topic. D. Infrastructure as a service. Yes, infrastructure as a service provides virtualized computing resources over the internet, including virtual machines. Let's take a moment to wrap up what we've covered in CCNA exam topic 1.2. Network topology architectures. We began by exploring SOHO networks, the small office or home office setups that often rely on a single device like a Wi-Fi router to handle wireless, routing, and internet connectivity. Simple, cost-effective, and familiar to most of us. From there, we moved into campus LANs. First, the two-tier designs used in medium-sized networks, then the three-tier architectures common in large enterprises, with core, distribution, and access layers providing scalability and resilience. We then took a closer look at data center architectures, especially the modern spine-leaf topology that's designed for high-speed, low-latency connections and efficient east-west traffic, the traffic between servers and applications inside the data center. After that, we contrasted how on-premises and cloud architectures work, with most networks today combining both in hybrid models. We saw how cloud has reshaped traditional concepts like the DMZ, allowing organizations to offload public-facing services and reduce their on-site attack surface. We went over the different cloud topology models in use today and how organizations can leverage them to increase flexibility, reduce costs, and streamline the delivery of services and applications. And finally, we compared WANs to LANs. While LANs connect devices within a building or campus, WLANs link branch offices, remote sites, and data centers across cities, countries, or even continents, often using leased lines, MPLS, or VPN over the internet. So where do we go from here? In our next video, we'll dive into CCNA exam topics 1.3 and 1.4, where we'll explore network interfaces, cabling, and essential troubleshooting skills you'll need to keep these architectures connected and running smoothly. Make sure you click that subscribe button so you don't miss it. And let's keep building your CCNA knowledge one step at a time.